All right, we're back with another lab. This lab is an introduction to acids and bases, basically weak acids. Only weak acids are really important or are really interesting to look at. And we're going to deal with the titration of a weak acid to determine its Ka. I'm going to give you probably a lot more information, certainly a lot more information than you need to do this lab, not more than you need to understand this lab. And this should help you in class. If you're going to be taking quantitative chemistry, that's my area of expertise, especially over the summer when I teach quantitative chemistry, the lecture for it, you'll need to know this stuff. So I don't know how they're going to present it to you in class. Hopefully they won't use something silly like ice tables to do acid and base equilibrium, because that's just disastrous when you get into really trying to understand it. I will show you the proper way to do it. How they introduce in class, that's up to them. But if you can understand this, you'll be really, really well off for later on in other chemistry classes. Okay, let's get into it. So first off, there's a couple of different definitions of acids and bases. The one we use the most is the Bronsted Lowry definition, which basically says that an acid is a proton donor and a base is a proton acceptor. There's the savant Arrhenius definition, which was the first one, and that's only good for aqueous solutions, which we deal with anyway. So either the Bronsted-Lowry or the Arrhenius definition both work for what we do, because we're only dealing with aqueous solutions. In aqueous solutions, base is going to produce hydroxides, and an acid is going to produce hydroniums. Now, they probably do your hydroniums as H plus in class. That would be a bare proton, right? Because what's a hydrogen atom? It's just a proton and an electron. If you take away the electron to give it a plus charge, then it's just a bare proton. In aqueous solutions, you don't have any bare protons. They'll always join with a water molecule to make H3O plus. And then, of course, they give you the definition of pH being the negative log of the hydronium ion concentration. Now, these brackets, if we haven't talked about that before, brackets are what are known as species concentration. That is, it is the concentration of that species in the solution. That's not the same thing as an analytical concentration, and I'll explain that in a second because it's very, very important with acids and bases and also with solubility. This is really not the true definition of pH, but it's good enough for GChem 2, close enough for what we do. So they did it as the negative log of the hydronium ion concentration. I don't know why they did negative log, but that means that the lower the pH, the higher the acidity. And the higher the pH, the lower the acidity, or the higher the basicity of it. And the reason for that is that water is amphoteric. It acts as both an acid and a base. And we can see that by if we have two water molecules, they can in solution, remember this is an equilibrium, they can in solution go to produce a hydronium ion. That's what sometimes will be given to you as H+, but really it's H3O+, plus OH-. Now you can kind of see this if you look at a water molecule, right? That's the oxygen, the hydrogens. It's got two lone pairs of electrons. So if I have two of them like this, well, I can take one of these and move it over here. And remember, what's a hydrogen? It's just a proton and an electron. So if I take these, this is a pair of electrons, right? These are unbonded pairs of electrons. This is a bonding pair of electrons. If I take that pair of electrons and move it onto the oxygen, move this proton over here, when the proton is sharing these two electrons, it looks just like a bond. This turns into, that's a hydroxide, and this turns into and that's a hydronium. So water can form hydroxides and hydroniums, and it does so naturally. It occurs to the level where the concentration of the hydroniums times the concentration of the hydroxides equals 1.000 times 10 to the negative 14. That's known as Kw. K, constant. That means always in an aqueous solution, the hydronium ion concentration times the hydroxide ion concentration equals 1 times 10 to the minus 14. That's going to be important, especially when we get into buffers and things. You need to remember that. Okay? So that's sort of the outline scheme of what's going on. Now let's get into acids and bases, weak acids and bases. So what's a weak acid? Every weak acid, no matter what its formula is, don't get hung up on the formula. If it's a monoprotic acid, only has one proton to donate, all monoprotic acids can be listed as HA. That's the hydronium and acid, right? That's going to combine with water in equilibrium to give us H3O plus A minus. Sorry, there's a big shadow on here, but there's no sun out this morning, so there's no light coming in from the window to offset that shadow. So this is the conjugate base, and this is the acid. All right. Now, remember, acids can donate protons. This donates a proton to water and forms hydronium. Bases can accept a proton. Well, this donated a proton. It can now accept a proton. So this is the conjugate base of the weak acid. All right. So this is what happens when you have a weak acid in solution. And we know that anything that has something like this, we can have a Ka expression, and our Ka expression is going to be products over reactants. We have hydronium concentration times A minus concentration all over top of HA concentration. We don't add water because this is in aqueous solution. And when things are in aqueous solution, you don't use water because the molarity doesn't change. It's 55.6 molar, and that stays in the Ka. Okay. So this is a complex equation because we don't know what H3O plus is. We don't know what A minus is. We don't know what HA is. We do know what Ka is. Let's do an example. So we'll do the first example in here with the thiophenol, and we want to know what the pH of, we want to find the pH of a solution that is 0.152 molar in this thiophenol. It doesn't matter what the formula for thiophenol is. You just need to know the molarity of it and then the fact that you can write it as HA. And then, of course, they give us that the pKa, what's pKa? pKa of this weak acid is equal to 6.520. Well, what's pKa? Well, pH is the negative log of the hydronium ion concentration. So P functions are basically the negative log of something. So if it's pKa, it must be the negative log of the Ka. Okay, so how do we get back to Ka? Because that's what we need, right? This is Ka, not pKa. So we need to get to Ka. We will use pKa later on. Well, we take the anti-log. Now, a lot of students don't know what the anti-log is in their calculator. Now's the time for you to introduce yourself to it. Because this is log base 10, it's implied that this is the negative log of base 10. We're going to take 10 raised to the negative of the pKa. Why? Because it's negative log of the Ka. Therefore, we must take the negative of that value to get the Ka back. And that's the negative of 6.520. And that gives us our Ka. And when we do that, we end up with 3.02 times 10 to the negative 7. Okay, so that's our Ka. Ka equals that. Okay, so we have 3.02 times 10 to the negative 7 is equal to our H3O plus times our A minus, conjugate base, all over top of our HA. Complicated equation because we don't know what hydronium is, we don't know what A minus is, and we don't know what HA is. So this is where we have to make some assumptions. First, we don't even have to make an assumption. First, we can just use Levassier's conservation of matter. How can we use that? That seems like a strange thing to pull out. No. Think about this. I know that the analytical concentration is 1.52 molar, right? That's the analytical concentration. Analytical concentration is usually given as capital C, and if I did HA, that would be 0.152 molar. Analytical concentration says, how many moles of this did I put into 1 liter of water? I put in 0.152 moles of this thiophenol into 1 liter of water. Even if we don't have a liter, doesn't make any difference. In this case, it didn't give us a volume, it gave us a molarity, doesn't matter. That implies that there are 0.152 moles, there would be 0.152 moles if we had a liter of it. That's called the analytical concentration. Well, that says we put in 0.152 moles to a liter, or there would be that many in a liter. And so that is going to be equal to, well, it can take two forms when it goes into solution, right? It can either be HA or it can be turned into A minus. So the combination of the HA and the A minus must equal the molarity that was put into solution. Once it goes into solution, all goes into solution as HA, but some of it goes to form A minus. For every A minus formed, an HA is lost, right? Because it takes one of these to go over here and form that and protonates that. So you got to get this concept straight in your mind. Really, it's really important to sit down, think about this, and make sure it makes sense. Make sure you understand it, because it's super important for everything we're going to do for the next 4 or 5 labs. So the analytical concentration is equal to HA, species concentration. That's the concentration in solution. I put in 100 moles of this. So many moles of it stay as HA, so many moles of it stay as A minus, but the sum of the HA and the A minus must equal the 100 moles I put in originally, right? Okay. Plus my species concentration of A minus. That's where species concentration comes in. The sum of the species concentration in this case must equal the analytical concentration. We know that. That's a given. So I can take this and I can say, well, therefore, HA, because I know what this is, right? This was given to me in the problem as 0.152 molar, so I know this value. HA then must be equal to what? It's going to be equal to CHA minus A minus. Okay, well, I can take this value and plug it in for HA there and eliminate one of the unknowns. Now I have Ka equals H3O plus times A minus all over top of CHA, which I know, minus A minus. Now I've only got 2 unknowns. I've got the hydronium ion concentration and the A minus concentration. I know what this is and I know what this is. So I've only got 1 unknown left. I've got 2 unknowns left. 2 unknowns left. So that's much, much better than it was. And actually, with this, I can, so now this is where we have to make an assumption. All right, no assumption made to get here. We just lose Levassier's conservation of matter. Now we have to make an assumption because we need to simplify it more. We need to get it down to 1 unknown. All right, so what assumption can we make? Well, let's look at this and let's see. For every hydronium that's created up here, an A minus is created. And for every A minus, there's a hydronium, right? The way we got an A minus was that the HA donated a proton to water and formed a hydronium. Therefore, every HA that reacts with water forms a hydronium and an A minus. Therefore, for every hydronium formed, an A minus is formed. For every A minus formed, a hydronium is formed. So if I eliminate or just ignore the self-ionization of water, which also forms hydroniums, but they're very, very small. Remember, the combination of these two is 1 times 10 to the minus 14. So if I ignore that and say that's insignificant compared to what's going on, then I can easily see that based on what's going on up here, I could say that my hydronium ion concentration is approximately equal to the A minus concentration, right? If there's one of these formed for every single one of these formed, then the concentrations must be pretty equal. So if I say that they're equal, then I can take this and I can say now Ka is equal to H3O plus times H3O plus over top of CHA minus H3O plus. Well, look at that. There's only 1 unknown. And actually for this, H3O plus times H3O plus, that's the same thing as H3O squared. So I can say Ka is equal to H3O plus squared over top of CHA minus H3O plus. 1 unknown. Bingo. I can solve for that. That's not a problem. What can I do? Well, I can rearrange, I can solve for this and it becomes a quadratic equation, and you should know how to solve a quadratic equation. So if I solve it as a quadratic equation, I end up with hydronium ion concentration plus squared plus, Ka times hydronium ion concentration minus CHA times Ka equals 0. That's my quadratic equation. What's CHA? Remember, CHA is the analytical concentration. I was given that. So this then becomes H3O plus squared plus what was my Ka value? My Ka value I determined was what? It was 3.02 times 10 to the negative 7 minus, and that's the CHA times Ka, that's the 3.02 times 10 to the negative 7 times my 0.152 molar equals 0. Remember, Ka and CHA is this 1.52, Ka is the 3.02. So I've got the analytical concentration in here, Ka. And if I solve all that out, throw away the extraneous root, I get a hydronium ion concentration of 2.14 times 10 to the negative 4 molar. And that gives me a pH equal to 3.67. Okay? Quadratic equation. That's an example of a weak acid under what's known as initial conditions. That is, it's a weak acid and there's nothing been done to it other than it's just been taken and thrown into the beaker, and we want to know what the pH of that weak acid is. Obviously, the pH is dependent upon the concentration of the acid and the Ka of the acid. Ka is going to have a very important effect upon it, just like the concentration of the acid would. Okay, there is another simplification you can make to make that even easier, but I'm not going to get into it. It just complicates things a little bit. So let's look at an example that has to do with what we're doing today, kind of. You could use this to determine what the pH was going to be along the equation. Let's see what happens when we add a strong base, sodium hydroxide, to a weak acid, okay? So we're going to calculate the pH of 25 milliliters. In this case, we need to know the volume. 25 milliliters of a 0.120 molar solution of acetic acid has a pKa equal to 4.75. And we're going to do additions of 0.00 milliliters, 10.00 milliliters, and then that's going to be of 0.105 molar NaOH. And then we want to know what is going to be the pH at the equivalence point. Okay, the equivalence point. So let's get going on this. We have everything we need to do for the most part. There's a couple little things, new things that'll be introduced in here. And I know that this is going kind of quick. You can go back and watch this video again. And I know that this is more information than what you really need to be able to do the lab, but it is important information, I think, that'll help you hopefully in class. So we're going to start off with what? Well, first thing we're going to do is zero addition. So that's initial conditions. That means it's just like the thing we just did. We're going to have to find out what the Ka is. And the Ka, if we do the calculations, and you can go ahead and do that, it's going to be 1.78 times 10 to the negative 5. Remember, we take the negative anti-log and do that. Then we set it up. We're going to have our 1.75 times 10 to the negative 5 is going to be equal to our hydronium ion concentration times A minus all over top of HA, because remember, it's always any weak acid monoprotic is going to be HA plus H2O gives us H3O plus A minus. That's the equation we're working with. That's the Ka, products over reactants. It's all in there. We solve the quadratic. The quadratic always ends up being H3O plus squared plus Ka times H3O plus minus Ka times CHA. So I did the CHA first, sorry, equals 0. So in this case, that gives us H3O plus squared plus Ka. What's our Ka? 1.78 times 10 to the negative 5th minus 1.78 times 10 to the negative 5th times our CHA, that's our analytical concentration. Our analytical concentration doesn't matter how many milliliters. Analytical concentration was 0.120 molar. So 0.120 molar in here. We solve that quadratic, And we get hydronium ion concentration is equal to, what, 1.45 times 10 to the minus 3 molar. And therefore we get a pH equal to 2.84. Remember, always kind of check yourself by looking at it and making sure it makes sense. This is a weak acid. pH should be below 7, and it is. 2.84. Weak acid, still pretty low pH because there's nothing to offset it from reacting in there. But that still is that's still an indicator that we did something correct. Again, I'm not going to get into the other assumption that we could do. I'll just tell it to you. I won't go through the assumption, but when we had our equation that we ended up with, and this was our equation right here, right? We can make one assumption, and that is that the analytical concentration minus hydronium ion concentration here, that the analytical concentration is much, much larger than the hydronium ion concentration. Very easy assumption to make. You have to check it and everything else. If you do that, you can see that this equation then becomes that the hydronium ion concentration is equal to the square root of Ka times CHA. Wow, that's easy. Hydronium's is square root of Ka times CHA, because I just took this, move this over here, take the square root to get rid of the squared sign there, and this works most all the time. You have to be able to check it, but it is a good thing to do. Let's see if it works here. We're going to say the hydronium ion concentration is going to be equal to the square root of our Ka, 1.78 times 10 to the negative 5, times our CHA, 0.120. Well, if we plug that in, what do we get? If we plug that in, we get 1.46 times 10 to the negative 3 molar. Well, the negative log of 1.46 times 10 to the negative 3 molar is going to be 2.84. We got the exact same pH. How about that? That works. That's a really good trick. Again, there's assumptions that are made to go into there that have to be checked and stuff, but it does work, and it's a good one to know. If you're on an exam and you need to find the pH of the initial conditions of a weak acid, that means the weak acid put into a beaker, that's all that was done. You know what the analytical molarity is, you know what the Ka is, or the pH. You can figure out what the pH is for a weak acid. The biggest thing is that the Ka should be smaller than something times 10 to the negative 3. In this case, our Ka was what? Times 10 to the negative 5. So that's much smaller than 10 to the negative 3. If it's 10 to the negative 3, this probably won't work. So you got to be careful of that. But that's a really slick trick to check yourself on an exam. If it's multiple choice, you do this real fast. If you get a pH, well, they might try to trick you. I don't think they would do that, though. All right. So hopefully you understand this and you got this down, that's the initial conditions. I know I've gone through this kind of quick. It's usually quite a bit longer in lecture, but hopefully they've covered this in lecture, and I'm just giving you kind of a refresher in there. Now, let's think about what happens if we add 10 milliliters of strong base. Well, let's think about this. Remember, we've got HA plus H2O goes to give us H3O plus A minus. Now we're going to add in a strong base, sodium hydroxide, NaOH. NaOH is a ionic compound, and we know, I think I've done this before. If I haven't, you got to do it now. Your mantra is ionic compounds go into aqueous solutions as their ions. What goes into solution is not sodium hydroxide. What goes into solution is sodium plus hydroxides. We don't care about the sodium. Doesn't have any effect on what we're doing because our equation doesn't have any sodiums in it. And you say, yeah, but it doesn't have any hydroxides either. But remember, H3O plus, I keep breaking the tip on my pencil, plus OH minus goes to give us water. So, for every hydroxide added in, it can react with a hydronium to produce water. So that means every hydroxide added in would get rid of a hydronium and create water. This would be reduced, this would be increased, even though increasing this doesn't really affect the equilibria. Still, this is reduced. What does that remind you of? Le Chatelier's principle, right? Remember? Equilibria. If I'm reducing this, it's going to drive the reaction in this direction. So, as I add in sodium hydroxide, I reduce the number of hydroniums. I drive the reaction in this direction. That creates more A- and reduces the amount of HA present. Remember, we did our simplification. We had it based on the fact that we could substitute in that CHA, that for every A- formed, there was a hydronium formed, right? But that's no longer true, because now we're reducing hydroniums, which creates more A-. Now we have much more A- than hydroniums, and we're reducing HA. So we can't use that simplification. We can't use the approximation. We got to go back to what we started with, and that is Ka equals H3O plus times A- all over top of HA. We've got to use this equation. We can't simplify it the way we did before, because A- is not equal to H3O plus anymore, because as we add in hydroxides, they react with hydroniums to give us water. And that means they're removing hydroniums. The reaction shifts to offset it, create more A-, more hydroniums, reduces HA. Oh my gosh, we've got a mess. Now it actually makes it even easier. You'll see. Okay, so first thing we want to do is, well, what do we want? We want pH, right? So let's arrange this equation so it solves for pH, and pH is by hydronium ion concentration. So hydronium ion concentration is going to be equal to Ka times HA all over top of A-. Okay, if I take the negative log of both sides, I get pH is equal to pKa. Hey, pKa comes back. Plus, remember logs, when you multiply, you add them. And this is we're adding negative log. Remember, this is P means negative log. I'm taking the negative log of HA over A-. But I want to do it as addition. I don't know why they did it that way, just because it's easier, I guess, for addition. So I use the rule of logs. And the rule of logs is that the negative log of something is the same as that something 1 over, the inverse of whatever it is. So if I change this to a positive log base 10, I'm going to have to change this to A- all over top of HA. Okay, well, I want pH. I know what pKa is. I know what a log is. All I have to do is figure out what must be A- and what must be HA. But how the heck can I do that? Because when I first put it in, it formed some A- and we lost some HA. And now I add in hydroxides. I'm going to change the hydroniums. There's going to be more A-. There's going to be more HAs lost. I don't know what to do. But for every mole of hydroxide added, a mole of hydroniums are lost. And therefore, a mole of A- is formed. For every mole of A- formed, a mole of HA is gone. But let's not use moles. Let's use something that makes it a little bit easier, and that's millimoles. And I hesitate to introduce these, but it's so much easier if you can use millimoles. What's a millimole? A millimole is just 1,000th of a mole. And the reason we want to use them is because you know that molarity times liters equals number of moles, right? You know that. That's the M1V1, whatever. Well, molarity times milliliters equals number of millimoles. And that's so much easier because everything always goes by milliliters. Nobody uses liters anymore. That's bucket chemistry that went out in the 1900s. So, well, you're going to use millimoles. As long as you're consistent and don't try to go back to liters and moles, you can use millimoles in these equations because remember, they're divided over top of each other. Okay, So what does that mean? Let's go back to our equation. pH equals pKa plus log of A minus over HA. A minus is going to be equal to the number of millimoles of OH added. Why? Because for every millimole of OH added, a millimole of hydroniums are removed, and therefore it must shift to create a millimole of hydroniums back on the equation, and that creates a millimole of A minus. So my A minus concentration up here is equal to the amount of hydroxides added. My HA then is my initial number of millimoles minus the number of millimoles of OH added. Why? Because I had so many to start with. For every millimole of this added, one of these are removed, one of these has to shift to form that, and therefore this is reduced by that number. Let's say I have 100 of these to begin with. I add in 25 millimoles of OH. That removes 25 millimoles of hydroniums. This must create 25 more millimoles of hydroniums. That makes 25 millimoles of A minus and leaves me with 100 minus 25 millimoles of HA, or 75 millimoles of HA. The other advantage of millimoles is, yes, this is species concentration, but notice that's what? That's millimoles per milliliter. Same thing as moles per liter, millimoles per milliliter, over millimoles per milliliter. But it's the same milliliters. So the milliliters cancel out. I just need to put millimoles in here. I don't even have to mess with the volume. Wow, that makes it easy. Again, you got to do this and make sure you understand what you're doing, because it's easy to mess up if you're going with moles and stuff like that, moles and liters, and then trying to switch to millimoles and milliliters. But as long as you keep it consistent, it's okay. All right, so let's see what our problem said. Our problem said we added 10.0, wasn't that what it was? 10.0 milliliters of our NaOH solution. What was our NaOH solution? Let me make sure I can find it. Let me make sure I find where we are. We added 10 millimoles, and it was 10 milliliters of a 0.105 molar solution of NaOH. That means that creates 10 times 0.015, which is 1.05 millimoles of OH minus, which equals A minus. But how about HA? Well, HA is going to be equal to the initial number. What's the initial number? Initial number was we had 25 milliliters. Remember, it gave us number of milliliters of acid. 25 milliliters times our concentration of our acid, which was 0.120 molar. That means we started off with 3.00 millimoles of HA. Remaining, we have our 3.00 millimoles of HA minus our 1.05 millimoles of OH minus added, gives us what? 1.95 millimoles of HA. Well, now we've got everything we need. pH is equal to, well, what was the pKa? Remember the pKa? We used that initially to do what we did. It was what? 4.75. It's 4.75 plus log base 10 of A minus. What's A minus? That's our 1.05 millimoles over top of our HA. That's what's the remaining millimoles. That's 1.95 millimoles. Plug that in there. We get a pH of 4.48. That is simple. That's much easier than even doing initial conditions. Anytime you have a weak acid and there is any strong base added to it, you've got a buffer. That's what this is. This is a buffer. You use the Henderson-Hasselbalch equation. That's what they call this equation, the Henderson-Hasselbalch, even though it's really just Ka. And you just do pH equals pKa plus log of conjugate base, that's created by the number of millimoles of strong base added, over top of weak acid remaining, and that's the number of millimoles of weak acid remaining after you've subtracted away the millimoles of conjugate base that was formed. Because remember, to get A minus, you've got to remove an HA. So it's the total number of millimoles of HA you had to begin with. That's molarity times milliliters of your initial conditions, minus the amount of millimoles of A minus added, which is molarity of the NaOH times the milliliters of NaOH added. Okay? All right. So if you understand that a little bit, then let's consider what happens. I'm not going to go through the equivalence point because what happens at the equivalence point is, think about it again. I'll just mention it. I'm not going to do any calculations. I have HA plus H2O goes to give me H3O plus A minus. Now, what does equivalent mean? Equivalent means equal, right? So the equivalence point is when an equal number of moles of NaOH has been added as there were moles of HA present, or millimoles. If I add in the same number of millimoles of NaOH as there were millimoles of HA present, what does that mean? That means I've removed the same number of millimoles of H3O plus as there were HA. All of it shifts over here to form A minus. This goes away. My solution then becomes, these are all gone, my solution then becomes A minus plus H2O gives me HA plus OH minus, a basic solution. So what does that mean? That means at the equivalence point, the pH of a weak acid is never 7. Ever. Never, ever, never. It's always greater than 7. Okay? And well, we'll get into buffers. Buffers, I think, is next. After this lab, the next lab is buffers. Okay? That's at the equivalence point. Now, you got to make sure you understand the equivalence point to understand halfway to the equivalence point. Two different things. I know people, that's one thing the students always get confused between the equivalence point and halfway to the equivalence point. Why is halfway to the equivalence point important? Let's look at our equation again. Remember, pH equals pKa plus the log of A minus over top of HA. And remember, this is equal to the number of millimoles added, OH added. This is equal to number initial minus number of millimoles OH added. So if I'm half at the equivalence point, I've added an equivalent number of moles of this as there were of this present initially. So basically, all this goes away, it all becomes this. So if I'm halfway, what does that mean? I always like to do things like this with just really simple numbers so I can keep them straight. Let's say I had 100 millimoles of this. Halfway would be what? 50, right? That's half of 100. So if I added 50 millimoles of OH, I'd have 50 millimoles of A minus, and I'd have 100 minus 50 millimoles of HA remaining, right? Because I had 100 to begin with. I added 50 millimoles of OH. I neutralized or shifted them to conjugate base. I made conjugate base out of 50 of the 100 millimoles of my HA. So I now have 50 millimoles of A minus and 50 millimoles of HA. 50 over 50 is what? 1. This becomes 1. Log of base 10 of 1 is what? 0. This becomes 0, and pH equals pKa. So if I titrate my weak acid with a strong base, and I add in volumes until I get to the equivalence point, and I say, oh, okay, I reached the equivalence point when I added in, say, 36.52 milliliters. That was at the equivalence point. Then halfway to the equivalence point would be half of that. So half of 36 is what? 18.2, let's just do 18.25 milliliters. That's halfway. If I go back to where I added 18.25 milliliters and I look at the pH, that's going to be equal to the pKa, because pH equals pKa when the A minus and HA are equal. Log of 1 is 0. pH equals pKa based on the Henderson-Hasselbalch equation. Okay? Does that make sense? All right. If you have any questions about this, if you have any things, if I did something that just didn't make any sense at all in the video, let me know so I can fix it. I can do a Zoom and explain it to you. This is usually important stuff. It's going to be important to understand when we get into buffers. It's going to be big time important to understand this. So it shows up, and then we use things similar to this in solubilities and things that we're going to get into. So hopefully you understood what we did. Hopefully you can work it through. It does take a bit of work to do, but it's not that hard. This lab is not that hard. It's an Excel spreadsheet. You will download the spreadsheet, and then you will just titrate it. Now, you got to be careful. I didn't make up the spreadsheet. I list on there who made it up. I kind of modified it a little bit, but you can't lock the cells so they can't be changed. So if you can accidentally change a cell and corrupt the whole worksheet. If you do that and things don't work right, then just erase that copy of the Excel and download another copy of the Excel spreadsheet on there. And try not to do anything. Try not to push any of the buttons except for the ones I tell you in the handout. Okay, so you're going to go through the titration quickly one time to find out where the equivalence point is, then carefully to find out exactly where halfway to the equivalence point is and the equivalence point. And then you're going to do some calculus. Oh, I know calculus, but you won't have to do calculus. I've got you doing calculus without doing calculus to find out where halfway to exactly what the pH is at halfway to the equivalence point. That's the pKa. With that, you should be able to determine what the weak acid was that you titrated in there. And then there's a data sheet. Just fill that out. Put your spreadsheets of your titration, and then the derivative that you did inside there. Put those two those two graphs in there. The spreadsheet of your titration, so I can look it over and make sure everything went okay. And then just pick whatever your acid is with a couple of small calculations. Calculations are not hard. They're not as hard as what we did in here. They're very, very easy, very, very simple. And then good luck. And we're going to do buffers, I think, next week. Okay? All right. See you then.